Okay, here we're going to tackle what I think is the trickiest part of these calculator context questions, and that is average rate of change, or average values. Okay? So, average rate of change, we're going to start with an example you already know how to do. Average rate of change, remember, is essentially just our slope formula. So in this case, we have from t equals 0 to t equals 8, be f of 8 minus f of 0 over 8 minus 0. Okay? And you can evaluate that on your calculator. I'm not going to show you how to do that. You can either just type in the function twice or type it into the grapher and use that second calc function. The result is 3.462 is the number you should get, so feel free to pause and see if you can't reproduce that. And here, what are we talking about here? So read it if you haven't already. Bears in a forest in t weeks. So average rate of change is essentially y's per x, right? So in this case, bears per week is our unit, so it's kind of a funny unit. And what this tells us is we're essentially over this interval from 0 to 8, the number of bears in the forest is increasing by about 3.4 bears per week, which seems pretty quick to me. Okay, so this is nothing new to us. We ran into this idea way back when we were building towards the idea of a derivative. So this is, again, called an average rate of change problem. Now that we know about integrals, we can complicate this idea of the average rate of change and average values of a function a little bit. So here's an example of an integrals problem involving averages. Now, you don't see the word average in the text here, but I'll explain the connection here in a second. So we are going to integrate this function and multiply times 1/9 because that's what it's asking for. So that you can do on your calculator. And what I like to do here is just type it in all in one go. So I typed in the 1/9 in front of the integral, and then the integral from 1 to 10, and I typed in my function with respect to x. I'll let my calculator do that. Oops. Oops, I forgot a parentheses, I think. There we go. So that's my result, right? So 5.510, I'll round it to, is equal to that particular integral. So that math wasn't very hard. Units of measure, well, this is the sum of a bunch of L's, I guess, and L is the depth of snow on the ground. So L would be in inches. Okay, let's think about what this represents. So I'm going to rewrite this integral in a certain way. 9 is 10 minus 1, right? And notice my integral goes from 1 to 10 of L of t dt. Okay, so what this is the sum of all of the L values from 1 to 10 divided by the change in time, 1 to 10. Okay, so this 5.510, how we'd interpret this is the average, not the average rate of change anymore, it's the average value of L from 1 to 10. Okay, so what this looks like graphically is here is my line representing that average value. So notice, if this is my function L, the black line, that value that I just calculated is about right in the middle of all these values. And obviously, like the function being higher might pull it up, but the function being lower down here might pull it down. This is right in the middle. Okay. And then what my previous problem looks like graphically, my average rate of change, where I didn't do an integral, this would be, we have some sort of sine function. This would be a secant line, right? So this would be a slope of 4, 6, 2, 1 bear. Wait, 3.462 bears, or 1 week. Okay, so both of these deal with averages. It's important to start learning the difference. And we're going to return to this idea as we wrap up integrals and move on to some integrals applications. But I think if you're doing this lesson right now, you should be able to start to chew on these ideas a little bit. Again, the best thing you can do for yourself is every problem you do here, read the interpretation, because that's really what this lesson is about.